David Jacobini, Mark Pennington, the speaker of today. We are wondering if anyone is coming already. And the room is suspect, and most of the people will be online.
But he's still around Jacopo.
Yeah, because Jacopo is already he's looking for the volcanology students that should be here. At least the student in the master in volcanology should be here.
I guess so. Yeah.
Jacopo.
Put some of the
Okay, Jacopo Natale is a former student of us, now he's a researcher at another university here in southern Italy. And he also works on the campus there. He's a structural geologist, but he works also on volcano tectonics.
I'm a statistician, so I'm not going to
You were in the AGU?
EGU,
Yeah. But so part of your presentation.
Oh, okay, so he's a repetition. So now you have the good questions. So you have the good questions now because you have seen it at least.
I did fill the room. It was a small room.
Yeah, but then you had people there, they go there to listen to people. Now here, the problem is people here interested in listening. Okay. But as I told you, at least they 10x on the stuff.
yeah, in fact, I'm trying to change it. But I'm interested in
Okay.
There are many papers in the last few years about trying to have kind of probabilistic assessment. Very interesting. I'm not sure whether the papers I'm going to talk about will translate because they threw a shitload of dates on these things.
Stefano Vitale, Mark Pennington,
Nera.
oh, giusto,
Jacopo,
non la possiamo spostare sarebbe sì.
Nel campo il giro.
Torniamo
We always say hi Jacopo, because it's the only one of my age or more or less. Because my age is somewhere of
I have a problem with technology.
The number of messages we both had, and the wrong one of us has responded. Because I was sitting at typing in my talk. And Mac came back and said, I know nothing about this. you know maybe Tullio Rizzi. Did you ever heard about him? Anyway, he's a volcanologist, so working in a group of he worked a lot in the Ionian Islands, in Vulcan and stuff. And his name is Tullio, which is quite strange in Italy, so there are very few people who finish it. But the point is that there was the head of the financial management of IDP that was named Tullio. So he received many strange emails with very, very strange requests. He promised not to repeat to anyone. Because if you write a Tullio, it comes up this way. Yeah.
Yeah, the average of a lot of transport.
Good morning. So, posso prima era un momento, sono impressionato, ma no, ma perché mi ha costretto, mi ha costretto fino a un progetto. E io ho detto un sì troppo,
questo lo pagate con 2 settimane sì, però bellissimo progetto, è molto felice. Però sicuramente il problema è che a un certo punto c'è stato uno dei simpatici collaboratori di quella parte, che si è ritirato l'ultimo minuto non per colpa per un problema serio, quindi è dovuto cambiare anche il sindacato di caso studio, e questo ha fatto sì che non avessi mai 6 ore per prendere la macchina che io ero andato a Bologna per una settimana, non potevo permettermi 6 ore di macchina. E quindi ho portato mia figlia, ci è tornato a scuola oggi per tornare a
If anyone online can please confirm that the audio is okay, that the level, the volume is okay.
Yes, it is okay if you can hear me.
Okay, good. We will start in 5 minutes.
Okay, thanks.
No, magari di
Prefer, I can.
Sono stati solo sottomissioni. I documenti per l'AMPO.
No, we are going through the national review of the every 2 years, and they are organizing everything, because probably this year we will have inspectors coming here and they will check every single thing.
We're waiting the commission to respond to public science things that have been released. Which must mean it's a mess of both of them.
Oh, yes.
Marginal aspect.
Yeah.
And that's then some opinion about the content or the core.
Certo. Fa piccole.
Ah, sì, quindi farai la guerra.
Quindi sarai uno di quelli che ha fatto il tutto. Ah, è stato sorpresato per la non ricordo che
Prova, prova, prova. Is it better like this with the
Yes.
microphone?
It's good.
If you prefer, you can use this one. Okay, so in this case, I will put the camera here.
No, veramente inutile. Non è che mandano in e valutare il lavoro con lavoratore. Quindi se ne mandano in quindi è buono avere delle editori esterni in quell'ambito passare
Una massa di lavoratori dei senatori
quindi il discorso è chiaramente se noi non vogliamo noi altri vogliamo e anche non vogliamo
Downgrading del tipico della conferenza, quindi va un po' prima uno di Bologna e gli mette la vicina di mettere.
Yeah. Iniziamo.
Io mi sveglio e ho detto mi strano, perché pensavo che qualcuno di quelli che c'è una forma, c'è un obbligatorio quelli che rimangono, però Paola va a detto per scritto tutti quelli che no.
Start. You confirm that the volume is okay for now, just see the screen with the slide.
Well, the voice was better earlier. It's
Oh, so
fine.
it was better before. Okay.
Okay.
So we
now,
go.
now it's okay. It was a bit.
Okay.
Yeah.
Okay. Jacopo, I want the role of presenting, introducing the speaker. Here,
Yes,
with the microphone.
let's start.
Okay, this is really my hope to introduce Mark. We work together for a long time already, but he is one of the most impacting and important statistical technology researchers and professors. So he made most of the most impacting works about these type of analysis, and which has a lot of other expertise, is really deeply involved in multi-hazard and risk modeling. We spent the whole 2 days yesterday and today speaking about those projects, huge projects that the New Zealand government is funding about multi-hazard and multi-risk. So it's really a pleasure to introduce you, Mark, and I think that I'm really curious to see what is going to present. That is about an important thing that all the people working in the countries and risk to do until probably is working these big commissions that are set up when they have to do the hazard and the risk assessment for nuclear power plants, which involve a huge efforts. And so I'm really curious to see what he's going to present. So thank you for being here and giving this lecture.
Jacopo.
Laura.
Hi, Mark. The audio is not really good now. Actually, when you were talking, we could barely understand. So
Okay, so I will change the microphone and we will make another try. Okay.
No, I think.
Not really.
Okay, I'm hoping that you can all hear me now. This is going to be awkward.
Okay, this was okay for us though.
No, you did it. Okay. Does anyone have a cushion I can kneel on?
Okay, maybe if
Also, there is an echo, so that probably will stop when you close your microphones. Okay. So please.
All right, well, I'll do my best to be as close to the microphone as possible. This was, as Jacopo says, one of those once-in-a-lifetime opportunities, and I found it to be very professionally fulfilling. I have to take you back to the days of COVID. In 2001, New Zealand was locked in. You couldn't go out for any reason whatsoever without taking a chance of not being allowed back in. And I had an email
saying, would I like to talk about possibly being involved in a project? And I said, yep. And basically, Kevin Coppersmith, who many of the seismologists here will know of, because he produced one very, very highly cited paper. But he now goes and runs these things. His professional job now is running SHAC level 3 integrations, which is really interesting. So they explained the thing to me. I said, great, I'll come on board. And they agreed to pay our not very exorbitant prices, which was good. But luckily, we managed to get out of New Zealand just in time for me to take part in the field trip. And I was flying into Idaho Falls, which is, it's got an 11,000-foot runway for some reason. But anyway, flying over, and I thought, my word, this place is flat. And then in the middle of it, there are these domes, which are 500 to 800 meters tall, in the middle of 30 kilometers of nothing. And it really made an impression. And I thought immediately, we're going to have to treat these a bit differently to the rest of the hazards. So never let it be said that first-hand observation of the site is not vital. Okay, so brief outline of what I'm going to talk about. If those who want the written version, it's all there. It's a nice nifty 1,548 pages. If you're going to download it, find a quiet corner because it's 655 megabytes. It took 40 minutes to download. So basically, I'll talk to you about what the problem was, what the hazard is, what the data is, and then my part was largely the temporal modelling, although I meddled in a lot of things because the integration team is just that. You have people from all sorts of backgrounds being involved in the whole project. And it's that, there's that old joke that attributed to Ernest Rutherford. If the scientist can't explain to the cleaner who cleans his lab what he's doing, he doesn't know what he's doing. And so we had logic trees and all the team had to agree on the thing. So the expert in the particular area had to explain to all these people who might be lava flow experts, who might be geologists, who might be geochemists, what the whole thing was about. And that was the most dynamic and exciting bit about the whole thing, because you're talking to really bright people, and they had some surprising insights way outside their area, and I'm hoping I can do the same for them.
Oh, ecco. Allora, bisognerebbe mettere, no? Prima, seconda valutazione, io adesso non mi ricordavo le valutazioni che hanno preso alle altre prove e insomma una terza valutazione, e poi io pensavo le osservazioni che noi facciamo sui testi di metterli nell'ultima colonna in modo tale che li possiamo dare proprio ai candidati come valutazioni della commissione, in modo tale che loro possono migliorare l'elaborato da qui alla fine della commissione.
And this was the volcanic one. So we're basically looking at most of these things in the blue dots. What's the hazard there from volcanic eruptions? All right, so here we are. This is the Eastern Snake River Plain from there. That's the Snake River Plain. Eastern Snake River Plain starts about there. The yellow box is our area of interest. X marks the spot where the INL sits. There are two major elements. There's 50 kilometres to what's called the Craters of the Moon National Monument, which is the Great Rift Zone. It's rifting, producing quite a lot of volume of, it's the first place I've ever seen rafted scoria cones, if you know what those are. You get a scoria cone and then the lava comes, and the lava just carries the scoria cone for tens of kilometres. It was fascinating. And then, of course, there's that other little issue which might be interesting to those interested in Campo Flegrei. We're about 200 kilometres from Yellowstone. And so that was ruled in. Okay, so you're supposed to do a SHAC level 3, supposed to be done or updated approximately every 10 years for nuclear power facilities. It's a probabilistic hazard assessment. This is the first ever volcanic level 3 study that was ever done. So we were making up the procedures as we went along. First thing I had to do was get up to speed with US government regulations. Oh boy, if you're not able to sleep, start on this list. And we were told there would be a quiz and we would have to pass it before we were allowed to go on. So, and we got re-examined more or less on these every year. Yeah. And when we did anything, we had to actually trace it back to which bit of the regulations we were acting according to. So these things got cited a lot in the document. Okay, this is the shack level 3 diagram. And oh boy. But you know, some of the important things, basically, what I was part of the TI team, and we were responsible effectively for bringing everything together and writing a report. And as part of that, we could bring in resource experts, and these are people who came and talked to us. I was online at the time in New Zealand. Remember, I wasn't allowed out. So attending a 5-day, 8 hours a day workshop starting at 1 in the morning and going through to 9:30 in the morning it was a drag. So anyway, they let me out just in time for working meeting 2. So we had resource experts, and then basically we did a whole lot of things and conduct screening. That was very unsatisfying. I'm sorry for the tsunami scientists in the room, because the one hazard we were able to rule out was tsunamis. And we eventually considered that the HARs were in spite of the fact that the place was flat. So that was it. We screened out tsunamis. Gave ourselves a big pat on the back for that one. Okay, having got that, we then decided we had this list of things. Then we brought in more resource experts to fill in the data gaps and proponent experts with models. And that was the workshop. So talks, and this is sometimes the TI team acted as experts and sometimes as the TI team. We were questioning the experts. It was all very incestuous, but went on. Anyway, so this is when we did all the work. Basically, these were 5-day meetings. We basically put up and knocked down models. I'm not going to lie, beer was involved. And then basically this was our preliminary examination. We had to present our results to what's called the participatory peer review panel. And these are eminent scientists covering from stakeholders through to some of the hazards who weren't actually writing the thing, but were in the room for all the meetings. And they were allowed to say, no, you've got that wrong in the meeting. And we were allowed to say, what do you mean? And so we would have a dialogue. So all the thing was constantly being reviewed. And it was a dynamic I'd never met before and was very fascinating. Anyway, and then we got down to the business. And this is, you think writing a PhD thesis is hard. You try producing one of these reports in 3 months. Oh, well. Okay, so basically we take the screened in volcanic phenomena, get the data, basically produce temporal models, the when, the where, the what, combine it all. This is fairly standard. The idea was that we come up with basically annual probabilities of disruption to a facility. And because we weren't allowed to know exactly what was in the facilities, they drew circles around them for us. And anything crossing that boundary was a disruption. So we had a lot of data. Oddly enough, in the INL itself, they have hundreds of boreholes for all sorts of reasons, and they had the borehole logs. So we could actually had data there, but they didn't do many outside of the boundary of the INL. And the INL itself is a topographic depression which is sinking. So the lava flows in from outside. So that was a bit irritating. So somebody said, yeah, we've got no record of any events in the INL itself. We said, well, yes, but you've got 1 kilometre of lava flows in there somehow. So where did they come from? So we managed to get rid of them. So then basically we had to break all the hazards down to different types, come up with workflows to identify the probability of disruption from any particular hazard. Here's our data set. Basically, you can see there's very few vents inside the INL itself. We've got this area here, which is the Great Rift. And this is a topographic high. It's about 50 metres higher than the INL, across 50 kilometres. But the lava follows down the flow. It's amazing stuff. We actually, you know, the field trip, we went and looked at lava flows there, which is 30, 40 kilometers long. Okay, data and models, I've covered most of that already, putting it all together. So basically we had local hazards, so shields, fissures, scoria cones, phreatomagnetic domes, lava flow, tephra flow, intrusive dikes. That's all the local hazards. And then we had to look at the distal hazards, and Yellowstone was obviously one. There's another volcanic field a bit to the south, which could produce, and then the Cascade volcanoes. So if you looked at St. Helens, for example, we were looking at that, and anyway, there was a caldera-forming eruption in about 7,000, and we had to look at it. We had people out looking for tephra deposits from that. That's the level they're operating at. Okay, so we broke down the vents. We had 19 solicit vents, 3 of which were cryptodomes. And I mean, you can't miss these things. They are very big objects and lava domes. And so different sorts of hazards. There's, oddly enough, there is water on there. There's basically the Snake River, and there are some massive phreatomagmatic eruptions. We climbed up one, and it was quite a hike. But the vast majority of them are what they call shield volcanoes, which are anything from 5 to 50 meters high, and just produced by layers and layers of lava flows, and which spread out to, you know, as much as 600 square kilometers. These are big objects. So in part of this, we ended up creating a whole lot of really new techniques in volcanology. And my bit, which I'm going to talk most about, was building the age model and thereby estimating the temporal recurrence rate. I'll briefly touch on a whole new frontier in spatial density estimation, and finally, how we actually put this thing together in order to compute hazard. So you can see the scale on that, that's about 50 kilometers north to south. And this is a series of lava flows. Okay, data. We had the vent locations. There are problems. There are a lot of buried vents. So we have a lot of lava flows there without a vent pinpointed. So we never really solved that problem. Of more interest to the people doing the thing was the idea that some of these vents are multi-vent eruptions. And I tried very hard at the beginning to say it's not really going to matter, because if we have fewer vents, it means that the area of impact is going to be higher commensurately. And I was proved almost exactly right 3 years later. But they couldn't actually, we couldn't do that sort of calculation. It wasn't allowed in the rules. We had to consider it. Composition, largely what they call Snake River olivine theolites, which is a very primitive basalt. But there are some quite evolved basalts, and that did my head in for a while. But it goes all the way through to actual real rhyolites. So there's a lot going on. These are things in the field, and then you've got the rhyolitic caldera nearby. They tried doing size category. The problem is that so many of these shields are covered on at least one side. So one of our proponent experts came up with a very good model, which actually stripped back the shield to get the pre-shield DEM and thereby estimated the volumes. But we couldn't do it across the field, so we had to let that one go. And then we had age data. A number of them were actually during the Holocene. We have C14 ages for all of those, all of 11. A lot of potassium-argon ages, enormous amount of argon-argon ages. Problem was they were done by 2 different methods, all to do with what you do with the intercept. And we couldn't reconcile them. So we basically just agreed to accept them at face value, because nobody was prepared to offend the other side by pointing out that their method was wrong. They have, these people have this little union that they don't do that. And then the problem was, we've got 450, these are 75% of the events we don't have an age on. because even the US Department of Energy's budget is not inexhaustible. So what they did was they had an expert judgment thing, which put them into age groups, up to 200,000 years, 200 to 400,000 years, 400,000 to 780,000 years, older than that. And they put them in that. So that's what it looked like. And then I came up with an algorithm because I say, yep, we can't have this hard boundary. If you're telling me it's 199.5, I'm not believing you. So I came up with a way to actually spread it across the regions, which I then had to defend and have agreed. So then we worked on that. And then there's a lot of paleomag. And that was great for saying, no, these two vents can't be in the same event because they must be at least 100 years apart because the paleomag does not overlap. But this was complicated because this place is one of the world's great places for actually creating the scale. So there's a problem with potential circular logic going on. In particular, we've got this thing here, which is the big lost cryptocon, because they've got a date on this thing and it's got the wrong polarity. So we know there's something in there which we think is really narrow because nobody else has found it anywhere else in the world. Anyway, so that had effects. I won't talk about that. Okay, this was my workflow. So basically I've got all this data, the sample paleomag, the variation of inversals thing. So that gives us a series of constraints. For example, if it's positive, I can say it must be here, 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 or here. It can't be here, here, or here. You can see there's a slight issue there. Then we have ages, and we have a lot of stratigraphy. And this is where all the dirty work got done. So combined with that creates what I call the age model. This is something where we have a series of stochastic realizations of ages for all 617 vents, each of one of which is consistent with stratigraphy and all the data, but you can't average them. So they create variations. Then we create realizations. These you fit temporal models to, simulate from them, create probability forecasts, check they're actually consistent with the tectonomagnetic model, and finally link to the spatial models. So this was my workflow. All right, age of data. Well, stratigraphy we thought was absolute, and then we started dealing with it. Remember how flat this is. One of the working meetings, we broke up, and I went down with the geologists, and we drank beer and looked at geological maps. We did this for hours to actually get our stratigraphy straight. And eventually, the stratigraphy kept getting updated because the model I produced would come out and say, hang on, I've got a chain of events here where there's a contradiction. So there has to be one wrong stratigraphy in there. So I give them this chain of 20 stratigraphic realizations, and they would go around and check each one until they found one that was wrong. And then I'd run it again and say, that's great, but the problem's moved to here. This was horrible. Okay, age determinations, fine. A lot of things, remember, when you get an age determination, it's a guess and an error. For argon, normally distributed. So you can get situations like this where time is going that way. This is the older event by stratigraphy, but its date is younger. But remember, there's always going to be an overlap. So we can put the event in there. And this is very valuable because it gives you a really hard constraint. Paleomatic clues, dubious. Matching of lavas, the problem was, they're 93% olivine tholite. Yeah, okay. That's an olivine tholite. That's an olivine tholite. They're not different. They could be, 50 kilometers away, still not different geochemically. Too bad. All right, so here's an example. This is data from craters on the moon. It's a geologic map. And I've basically, you can't see it, but I've highlighted all the areas where there was something I could consider as age information. and these are the paleomagnetic ones. And this was the simple stratigraphic. Remember, this is only a small fraction of the events involved. This was a concept showing what it is. And these are all the things which have to be younger and older than others. And then if you put in the widest interpretation of these things, it gets even bigger. So very quickly realized there was going to have to be an automated process here. There has to be an algorithm involved. I can't build it from scratch. So how many? This was a small but of this is a brute force one. You can see I'm doing every age individually. No, this was not going to work. So this shows, interesting enough, as you add in more assumptions, it doesn't do anything about the fact that it's non-stationary over time. On the other hand, some of these errors decrease enormously because these are considered to be young. There's no actual evidence for it. They just think they're the same as something else when nearby. It looks young, so they put them as young. And when we put that in, decreases enormously. Now these things, they have very little handle on altogether, but they're considered old. So if we make them all older, then we get a lot more definition. So there was a lot of discussion about how much of this, I look at it and I think it's old, we can incorporate. Okay, so I came up with a simulation rejection algorithm. I don't want to run you through this, but the key point was that I established an extended stratigraphy. So basically, stratigraphy says X is older than Y. But if I've got something that has a relation with Y and X, therefore it must be in the middle. So I created an extended stratigraphy that put all the bounds on anything, no matter how many things it was pushed through. It could be a chain. Well, in fact, I'm not going to show you, but there was one class of stratigraphy which had 560 events in it, which had a relationship with something else in that class. So this extended stratigraphy basically put everything that had an order in an order. And that's a large piece of code. And then basically all the ones that have an age, we sample from the age and we check whether they match the stratigraphy. And if a pair are wrong, we throw them both out and resample them both, check everything again, and they might be okay, but one of them now may be inconsistent with something else. We keep throwing them out until we get a consistent set. And then because of this extended stratigraphy, everything else then has an interval we can slap it into. So this bit, this bit of the code goes very slowly. This bit goes like lightning. So we basically put the 150 events with ages into a stratigraphic order, and then we slap the other 400, 500 in immediately. All right, so results. Here's a sort of typical thing. This one has a younger age, but an older stratigraphy. So you see that basically we're sampling from just this bit of the normal distribution. So every age in there has one in there, it is older than in that same realization. And this one gets pushed down. And how far they can be pushed depending on what's pushing from the other direction. So it can't be cracked. These are the overall statistics. And remember I talked about age groups, that's their expert judgment. These is the age distribution with the age groups. And you can see when we get to there, we're more or less got. According to the tectonomagnetic model, which says that volcanism is continuous, that's fully observed. If you don't have that, then you get this weird thing when it goes up there. So the very old events are more frequent than the slightly younger events. And that comes back to that paleomagnetic scale, because there were intervals in there and we have a lot of normally magnetized events, which are probably young, but they haven't got ages on. And there's a big element in the scale around there where you can put something. So if it's normally polarized and you don't have an age, if they don't have an age group, a lot of them get stuck there, and that's what caused this artifact. So we tried to deal with that. Okay, once we have ages, our big question was, is space and time independent? Because if it is, boy, that simplified our job. So, and there's only really one truly spatiotemporal model available. That's the one Chuck Connor and Brett Hill came up with, and where this is the intensity. And they basically look at the number of events and divide it by the area and the time. So, and this thing can't be separated. And it's a fascinating thing. So what I did was I looked at time slices from 300 years in the past, 200, 100, through to present. And basically, these are showing that the features we're interested in are persistent. Yeah, the intensity just doesn't change. The pattern keeps going. So we said, okay, this is evidence, apart from this little issue there, because this is a Holocene feature. So we know, we took note we're going to have to deal with this lot separately. But otherwise, we said, oh, sorry, the colour scale is different on that. It is showing exactly the same thing. It's just that the colour scale goes from log minus 3.5 to log minus 2.5. All right. Having noted that craters of the moon was going to be a problem, we then looked at the location of the domes, because remember those really tall domes, they have different hazards. And they are significantly placed relative to the other things. What this does is it works out a spatial distribution based on your controls. This is an epidemiological thing, and sees whether the domes are actually in the same spatial distribution, and they're not. Okay, so we had to separate the spatial model for the domes. Okay, we're continuing to separate. The evolved basalts, this was craters of the moon. Yep, they're different too. Great, move on. And then we got to other problems, like these are the same composition, but they have a completely different spatial pattern within them. And when you combine them as one spatial model, what ends up is a compromise between the two, which is no good because the hazard is coming from here. So we had to separate those out again. So we're continually slicing. And once we'd actually separated the data into 4 bits, then everything was okay and we could do the separation. So this told me, it's okay, you just have to go off and do 8 temporal models. No problem whatsoever. Because remember, I've got 4 spatial groups and I have the event model and I have the event model. Okay, I can do this. Right, so 2 million years of data, highly incomplete on the older data. How much can we use? Okay, the older data is less accurate due to missing data. The later parts, more recent parts, are probably more relevant to the hazard, although if you have a long system, you can find it has long cycles where it repeats from earlier. On the other hand, we have to have multiple models. Remember, we had to do aleatoric and epistemic uncertainty as part of this. That was required. We need complicated dependencies, which we got there by basically slicing stuff up. The more complicated the model, the more data you need. There's no such thing as a free lunch. So I said, look, my more complicated models may be able to go to different lengths of the data. We're okay with that? They said, yes, no problem. So as part of the modeling process, I had to determine how much data I could use for each model and each data set. Okay, completeness. This is the domes. As you can see, they are very, very hard to miss in the eastern Snake River Plain. And so this line here is basically the domes. And yeah, it's pretty much constant over time. That was really pleasing. Validated the tectonic magmatic model. On the other hand, they have what they call spatter cones, which are very low objects and can easily be bowled over or obscured by a subsequent shield. So they should appear later in the record and not earlier. And this was another thing with the age groups. You see with the age groups, these are the non-spatter cones and these are the spatter cones. That's with the age groups. The spatter cones are all young. That's great. If you don't have age groups, you've got 2 million-year-old spatter cones, during which period the state of the plane has gone up by about 500 meters. So highly unlikely to have left them. So more evidence. All right, getting on to the temporal. This is all expressed in terms of point process intensity. This is effectively the instantaneous rate of eruption. So it's events per time interval multiplied by your time interval. Remember, we're talking about thousands of years between eruptions, and that gives you an annual eruption probability. So we've got the standard Poisson process. Everything happens at a constant rate, no surprises. This one goes back actually beyond Ho. It was by Bain and Engelhardt in engineering, but they adopted it for use in volcanoes. And the great thing about this is it incorporates a time trend. And that's very useful because we can take that trend under our tectonic magmatic model as representing the incomplete volcanism. So this represents our observed volcanism, which we have a trend in. We can go back further and extrapolate through. So that was considered to be quite useful. This model allows clustering, so do events occur in clusters? And this was immediately decided that we could use this for small areas, but it was not considered reasonable that an event 200 kilometers away could set up the conditions for another one. So that was only local. And then this one, Shane Cronin and I published for the Auckland Volcanic Field. It's based on the Hawkes process. And the idea here is that there's a thing called the mid-crustal sill, and that basically lenses arise from that. They can be quite spatially extensive, and then they generate a series of eruptions over some period of time. So that's what it looks here. Basically, we have these things, and it all adds up. So you can see you can get a clustering process there. The other ones, the Poisson process, constant over time. The Weibull process increases, and the renewal process gives itself a high probability after an event. All right, interpretation. Poisson process, very easy to interpret. The whole thing is random. It's all an assemblage of many, many small processes, no problems. The Weibull process you had to have a spatial component. Ideally, the rate of increase of activity decreases over time. Hopefully. We didn't want it to be continually increasing because that was going to be hard to explain physically. Weibull new process cluster model, the idea is that basically events occur in batches of a variable size. And meanwhile, so there's two processes going on. There's a process that controls the arrival of the batch, and then there's the processes within the batch. So the probability of another eruption could be you have to add for, is that last batch continuing? And what's the probability of the next batch arriving? And this was tied to mantle-derived recharge in our tectonic magmatic model, and everyone was happy. Okay, having done this, this is what we do. Basically, this is an example from another paper, but you generate multiple realizations. We've got 1,000 in this case. You fit the model to every one of the 1,000 realizations, forecast forward for that model data pair, and then you do a statistical distribution of all the hazard forecasts at the end. It's an ensemble process. So we'll just ignore that. Okay, the fit, we maximize the point process likelihood. So this is rewarding ourselves for giving ourselves a high probability at the point the event occurs. Great, you forecasted it. On the other hand, if I say, yeah, it's very easy to say I never miss an eruption. I will say the conflagration is going to erupt tomorrow, and the next day, and the day after. I will never miss an eruption. My false alarm probability is quite high. So this is basically penalizing ourselves for the false alarms. So it's a balance. So the model fitting, basically, it's trying to drive the model through its parameters to having an infinite intensity where the eruption is and zero elsewhere, which you can't do. Meanwhile, does the model fit the data? And here the question is not just does it fit the data, which part of the data does it fit? How far back in time can I go? Okay, and there's this nifty little transformation. You do this, there's your fitted model, and you do it from some time forward to present day. Sorry, that should be T, not a TI. Oh, that's T. This is so at each occurrence, we get a new time, a transformed time. And basically, if the model is a good fit, those transformed times should be a Poisson process of unit rate. Okay, and that's easy. We have tests. They should be stationary, they should be independent, and they should be exponentially, the interval should be exponentially distributed. These are really easy tests to do. So what we do is basically we get the realization and we slam these three tests in. Okay, now remember, we have a significance level. So if we have 1,000 events, we allow ourselves 50 of these events to fail the tests. In fact, 50 of these events should fail the tests. So we optimize the time we look back in to where 5% of the realizations fail the model. And that's how we pick how far back we can go. And we incorporate all those forecasts going forward, not just the 950 that passed it. Okay, so here's the results. So basically you can see how far back we went, 53,000 years, which sounds like a lot, but isn't here. That's for that process. That's when the stationarity finished. On the other hand, if we take the Weibull process, which includes non-stationarity, we can go back to 210. Now this one freaked me out. That clustering process can actually get back to 450,000 years because of the clustering nature of the thing. And I had to dig down into this. I spent days looking at the results just to convince myself this was true. And I ran it for all different ages. It was really fascinating. So it didn't make much difference with and without age groups, except that the Weibull process without age groups. Remember, we're not sticking all these people young, we're allowing them to be old, so we could go back further. On the other hand, if we go to all events, this was for tephra, because we didn't distinguish whether it's a dome or a scoria cone or a mar. They all considered to produce tephra, and we got back all of 8,500 years. This is strongly non-stationary, that process. Okay, and from there we could take the models, and so these are the annual eruption probabilities per 1,000 years. So we're talking 1/3 of an eruption per 1,000 years, or a 3,000 year return period there. The domes, kind of one every 400,000 years. So this was the really hard work, because we had to actually justify these things. Well, not justify. The propitiatory peer review panel were there to make sure that we followed the rules of the SHAC 3. And so we had to write this, and we were not allowed to vote. This is the great thing about it. We could not allowed to vote. We had to sit there in the room until the 7 of us agreed on the probability. And this was so we had a strong preference for using the age groups. But on the other hand, you know, remember we had to do the center, the body, and the range of all the estimates. And so we couldn't discard this because it contributed particularly to the range of hazard estimates. For the craters of the moon, we had no particular preference among these 3 models. That was fascinating. Other places, we had very strong preferences on models. And then each one of these models, I handed over 1,000 hazard estimates, and these were converted into 9-branch logic tree. There's a series of papers on this apparently, which it was black magic, but basically they put a normal distribution on and they checked that they satisfactorily modeled the variance through this. And so they wanted logic tree branches, they got logic tree branches. You'll have to move me forward. I think I'm out of the loop now. Okay, so that was the temporal one. Okay, I'll just briefly talk about this. those of you going to IAFC, we have an invited talk from Chuck Connor on this. But yeah, we weren't terribly happy about the kernel density estimation. And those of you who saw my talk at EGU would understand some of my reservations. But yeah, we're working for the US government here. There is money. They flew a magnetic survey for us. They couldn't go over craters of the moon because the US Park Service is more politically powerful than the Department of Energy. But they did this, and we had the gravity survey, and we had a strain model, and what was the other one? Oh, the topography. And Chuck and his son and his wife produced this thing using a random forest, which combined all this data, which outperformed any kernel density estimate we had. So the only question is how much this is because the magnetics, obviously, if you get basalts, which are normally magnetized, that's a big thing. So are we saying where the event was or where the event will be? So for that reason, the logic tree, and boy, there were arguments here. So basically, we put 50% on the random forest because this is a completely new idea. It hadn't been peer reviewed. It hasn't gone out to the scientific literature. Chuck's, we've got the paper coming out through USGS. So it has been peer reviewed now. And we go to spatial density. And when you go to spatial density, there's adaptive kernels, composite kernels, and kernel density estimates. And these all got weights. And then we had to do with the vents. So you can see why the logic trees were incredibly convoluted by it, because this is just a very small part of the problem. And this had to be done for every vent set, had to be done for every hazard, had to be done for every facility. Anyway, so see Chuck's talk, be fascinating. Then, okay, so we know the when, we know the where. Okay, what about the what? Okay, Mike Lort is going to be talking at IFC, but basically what we did was we divided up into scoria cones, phreatomagmatic maars, domes, shields, lava fissures, and basically worked out, okay, what's the spatial distribution of the near vent hazard? Okay, and we started off, okay, we've got ballistics and gas out to 3 kilometers. Basically, something's going to happen. This was fascinating because we had a lot of very frustrating talks with the INL engineers who were very cagey about what their standards were. Yeah, so they talked about, oh, we set up for snow loading with this. You can use that for ash, can't you? Yeah, and no, we don't like ballistics. And oh yeah, if you tilt the facility, it's going to be really bad news. And that was what we had to deal with. So anyway, then basically things like this. We broke the shield down into the edifice itself plus the lava flow. We modeled them separately. So basically we put a disk down, an idealist disk for the radius, and these are the radii of the shields going out to 8.5 kilometers. Oh, sorry, the diameter? No, radius. These are big things. And then the lava flow would go on further. And we basically put a distribution on that, and that's that one down there. That's for the burial. Okay, obviously for burial facility, it's no good anymore. We did this for all the hazards. All right, then we ran into another problem. We suddenly realized that these small spatter cones don't actually occur on the INL. So we had to have a separate distribution for the ones that were for the near vent hazard, because these things are not producing near vent hazards over here. They're nowhere near them. So we had to go back and use the really big ones. So basically spatter went down, shields went up, scoria cones went up, and the phreatomagmatic stayed the same, which was interesting. Anyway, believe it or not, these things were actually then represented as logic trees. There's 3-dimensional logic tree going on. It was fascinating, and I will not present that because I'm not sure I understand it. Okay, this is lava flow modeling. Again, it's going to be a poster at IFC. But basically, we had to have experts come in and write us reports on all the available lava flow models. And we wanted to do hundreds of thousands of simulations. So these things had to be quick. Okay. And we have no idea what the parameters were going to be. And we have almost billiard table flat topography. So we very rapidly went down to molasses, which is very simple, very quick, and which has been validated on volcanic eruptions elsewhere. So for molasses, we need residual thickness. Well, that was fairly easy. We need to put in the volume, and we need the pulse volume. And then we realized that we tried forever to get the volume model into it, because the volume was the thing we didn't have due to burial. But what we did have was a very good estimate of area. And then Chuck had a brilliant idea. He said, we don't need to simulate these things forward. Okay? We don't put down vents, simulate things, did it hit anything? He said, we're only interested in these sites. So what I'm going to do is I'm going to simulate huge lava flows from every possible location in the INL. And I'll put that in the library. And then we say, I have a distribution of area. And we say, what was the area of the flow at which that location hit this site? And we just cut it off from the query of the library. So we generated a huge library, and then we just queried it stochastically to get the hazard. It's a brilliant idea, but it only works on a site-centered model. So the fact we only had 9 sites was the vital thing. So 4 pulse volumes to try and get somewhere between blobby and fingery. Because, believe it or not, there is topography in the INL. And the weird thing was, there's a thing called the Big Lost River. And basically, it's about this deep. But it's quite wide. And 3 of the sites are actually sitting in it. And it basically, there's a large area of the plain whereby you have a lava flow and it just gets into this and goes straight down. Fascinating stuff. Anyway, this was the area I corrected for the imbalance between shields and other things, and for burial versus non-burial, and came up with a model. And this is a really good fit to the data we have. Here's an example. So this is basically, Intec is one of those sites I talked about. And so you can see there's a topography that's driving in there. But yeah, this is a ridge. It's probably about 2 feet high. And then there's all these things up in here, and they start with down quite a slope. So no hazard from up there, because that's coming uphill, but this is the Great Rift. And at the top of the Great Rift, it can get down there, and that's 50 kilometers. Okay, and then we did temporary hazard, and yeah, we shamelessly stole the whole thing from Jacopo. We basically just created a tephra library and just moved it around the plane. No problem. So we had we had to do mass, we had to do height, plume shape, TGSD, diffusion coefficient, wind field. So this is how we get 30 million simulations. And we just used it the same way. We looked at this site and said, what's the probability distribution over all these factors? And is there anything in there that hits it? Oh boy, that was the easy bit. What do you do about the non-visible hazards? Okay, because there are what they call dike pairs out there, which go on for 20 kilometers. We actually drove along a set. And these are things basically, you've got subsidence in the ground, and any sort of horizontal or vertical dilation is very bad for nuclear technology. They don't like that. Okay, great. Very strong azimuthal thing, excellent. So we came up with footprints for large, medium, and then we came up with even bigger footprints for events. And these went out to something like 36 kilometers. So if we had a chain of vents, each with a okay. Are they online?
to reshare it, because we are losing connection at the point.
Okay.
Next slide.
In the volcanological fairy tale, we started looking at sills, and we had to give that one up. Dome intrusions, these are all things we had to put a number to, and they ended up being pretty rough. And just if you forgive me a few minutes, I'll talk about ignimbrites from Yellowstone, and drawing no parallels whatsoever to Campi Flegrei. Move on. Okay, the Yellowstone track, this is 40 million years, and basically it's been going across the eastern Snake River Plain for 10 million years. And this is what led to all the basaltic volcanism which followed on from the rhyolitic one. Okay, unbelievably, we had 50 ignimbrites, 43 of which have been dated. And Mark Anders in particular has made a lifetime study of this, and it's unbelievable, his data set. Problem is, some of these are one exposure, which might be in a core. The really well-known ones might have 3 exposures. So the size of these things is a big guess. So we came up with this scale whereby we'd put them in classes. So ranging from basically 75 cubic kilometers up to 660 cubic kilometers, but there are ones that are bigger that they have actually put volumes on that go into the 3,000 cubic kilometers. Okay, I won't talk about that. Oh, the one key was we were able to grab another couple of models because now we actually had data we could use the volume to see whether they had an effect. So I grabbed one of Varna's and one of my own. And here's an example of the fit, which is quite pleasing. I'm lost again. Can you go forward? Okay, then the eruption volume, and again we fitted to it. And the key thing here is we have a very mixed modal distribution. These are the little ones, the 100 cubic kilometer type stuff, and these are the ones which really do a major terraforming exercise. And if we had one of these from Yellowstone, it can impact the INL, and this was the bit we were interested in. Okay, and then we had to model it, and believe it or not, we tried all the usual things. Molasses does a fantastic job in modeling PDCs. You just give it one huge pulse and tell it to go forward, and the critical thing is the residual thing, and you just say how much topography you want it to be able to overstep. And it produces, we calibrated it against the Huckleberry Ridge TUF and got a really good agreement. Bearing in mind we were using a post-event DEM. So thank you very much.
So I have to apologize for you online because we lost connection at least 2 or 3 times. I think that someone is working on the connection because we have been without any Wi-Fi during the last week. So probably they decided today to work on the connection. Okay, so we open the question and answer session. We start with people here in the room, and then everyone that is online. You are free to open your microphone and ask questions, but we start here from the room. So any question from the room?
One simple question is the weights for the alternatives and the selection of the alternatives actually implemented in the logic 3. How was made? Because the only thing we were allowed to do was discuss and agree. It didn't matter what we brought into discussion. We could not vote. There were some things where we actually had statistical models and probabilities, and they accepted those. But for the ones where there was no model, we had to debate and agree.
And this was among a big group or just
there was 7 of us. 7. Yeah.
Okay.
Arranged. So I was basically there to do the temporal and statistical things. You had Chuck Connor, who was doing the spatial, and in fact we had an introduction thing, and I explained that my role was to argue with Chuck, and Chuck replied that I did it so well.
And the participatory review and also this, so the choice of the branches and the weights or not?
No. They were not. They were there to ensure that we did it correctly according to procedure.
Okay, but they didn't review that choice.
No,
Okay.
it was a choice, and we actually got in a lot of trouble about whether an eruption from Yellowstone is possible. You've seen there's a lot of papers saying that there isn't a large enough magma body down there. But remember, we're doing this on a 100-year forecast. And there's also a lot of literature saying how fast these bodies can assemble. So in the end, we basically said 20%. Because we said it's unlikely, but not impossible. And that was where the scale landed. And they accepted it. I'm sure that many of the disciplinary peer review panel had very strong opinions, but that wasn't their role.
Okay.
Okay.
When you were doing that weighting, did you review the weights?
Can you please repeat the question?
Gary has asked whether the weights were a one-off proposition or whether they were reviewed. And yes, we did a preliminary presentation of results, which were actually run through the hazard people, and it came back, and we got to see these, and then we had to go back and revisit every weight in the light of the hazard that came from our set of weights. Good question, thank you.
I didn't get, so essentially you had a multiple choice for weights, and then you looked at the results, and so based on how satisfactory it was for you for the group, I mean,
it's feedback. I mean, we had to do a preliminary model. It was a bit simpler. Some of the things went in there, but we had to provide weights so they could run it. And then we had this meeting where they reported back on what the hazard estimates were. And we had to review those and then go back and review, because it's really interesting because they dig down into what, and they can tell us the factors which are driving the hazard. And we had to go back and revisit. And in most cases, we retained our weights. But there were a couple of cases where we thought, no, we don't believe that it's that important. But the whole thing was just a matter of debate. There was no recording of minutes. The only thing the PPRP who were in the room said was, yes, it was debated and agreed. That's it. It was very much, nothing was said outside the room.
Okay. Any question from the audience online? Just open your microphone. You wish to ask a question? Okay. So if there is no other question, we just go for lunch. Okay? And thank you again, Mark. Thank you.
Thank you.
Thank you.
Thank you all for attending, and sorry for the